Hello my friend, today we keep going on with a little bit of recursion. We start with the classic easy peasy factorial problem. So vim factorial.c include stdio.h, and I hope you know what is factorial, but just to be everyone on the same page, just a little crash course. Basically, when we say factorial, we imply something like that. N factorial is equal to n multiplied by n minus 1 per n minus 2, right? And so forth until we multiply per 2 and per 1. This is the basic formula of factorial. To make a clear example, we have the number 5 factorial. It means that we have 5 per 4 per 3 per 2 per 1, okay? As you can see, the number is gonna grow very, very fast, right? If we have 100 factorial, this is gonna be a gigantic number. Why this factorial is useful in real life? Well, with this you can count permutations. To be clear, we have, for example, 3 people: Alice, Bob, and Charlie. Thanks to factorial, so 3 factorial, which is equal to 3 per 2 per 1, which is equal to 6, I know that I can have 6 permutations. Permutation simply means the way in which I can arrange these people. To be clear, one permutation can be this one: Alice, Bob, Charlie. Another can be this one: Alice, Charlie, and Bob. 3 can be this other one, right? Bob, Alice, and Charlie. And you got the point, right? You have all these possible permutations, all these possible arrangements. So long story short, factorial is telling me how I can arrange a collection of things. Now, before we jump into the code, we have to keep in mind that 1, the definition of factorial is only for non-negative numbers. And second, factorial of 0 is 1. Now, if you want to understand better this point, there is this marvelous video from this channel, Eddie Wu, that I highly suggest you to watch. And in general, this channel is bananas. It's super well done if you want to learn more about math. All right, cool. That's the idea. We have to code this function, factorial. My function is going to return an integer, even though factorial is going to grow very, very fast. We just want to understand recursion here. So integer, factorial, and as an input, I have an integer, okay? And b. Cool. Inside, I have my function definition. Now, let's write the main. So int main, and with a stupid for int I equals 0, I minor than, let's say, 20, plus I. I'm gonna printf %d, a new line, another %d here, and an arrow maybe, and here I put I, and here I call factorial of I. Cool, so this is my main test. Now, let's implement the function. So I have to do something like that, right? If I have a 5, I have to do all these multiplications. So I'm gonna stock inside an integer my result. And inside my result, I'm gonna put the value 1. 1 because this is the neutral value for multiplication. I cannot use the 0, otherwise this is not gonna work. Then I have to check for exceptions. So when the number is minor than 0, what do? We just return 0, okay? The definition doesn't imply negative values, or maybe it's better to return -1. So if number is minor than 0, we just return -1 to express that there is a mistake. Okay, so we are done for negative values. Now, here I can say while nb is major than 0. What do? While nb is major than 0. So here you will have 5, then 4, 3, 2, 1. You see? So I'm going to do while nb major than 0. You can do result per equal nb. Okay, and then I'm of course decreasing nb. So prefix decrement nb. You see? So I will have initially result per 5. Then I'm going to have per 4. Then per 3, and so on, right? And everything is going to be accumulated inside my result variable. So at the end, I'm just gonna return result. Now, when I have as an input 0, what is going to happen? I'm gonna skip this, I'm gonna skip this as well, and I'm gonna just return the result, which is 1, exactly what I want. And the input is 1, I'm gonna just multiply, I'm gonna just enter this while, right? And b is major than 0, yes, it is a 1, so I'm gonna do result per equal, what? 1. So 1 per 1 equals 1, right? So here basically I can also say major than 1. Okay, this is totally the same. And I think that's it. Now let's try to launch this code and let's see if it works. Oh, it's easy. We're gonna run factorial. Okay, it seems like that is working. I have 1, 1, 2, 6, 24, 120. Of course, the number is gonna become crazy big immediately. So here I get an overflow. Let's just watch till 10 if it's correct. I have 1, 1, 2, 6, 24, 1, 1, 2, 6, 24, 120, 720, 5040, and it seems like it's working properly, right? 40,320 and so forth. Cool. So we have an iterative solution for factorial. Now let's try to tackle this problem with recursion. So I'm gonna comment out this and I'm gonna do the same. So int factorial int nb. Now every time we do recursion, we have to think about two things basically: the case base and the recursive case. The exit condition, there can be more than one, and the recursive condition, basically when we call the function itself. We do case base exit condition, which is something like that. If something, you're gonna exit, okay? So else, you have the recursive case in which you are gonna handle all the recursion. Something is repeating. So recursive call. All right, in factorial, how can we tackle this problem in such a way? So what is the least amount of work, the easy thing, the case base? Basically, you can also say the easy thing to do, because we want to divide and conquer this problem, right? We want to make easy, manageable chunks exploiting the stack discipline, right? Inside the stack, we're going to exploit all the functions. All the functions are going to share a little of the work. So let's think about the exit condition here. I have my 5 factorial, right? Which is equal to this operation, right? When this operation is going to finish, even in iteration here, when we are going to finish with the multiplication, when NB is going to be 2, right? This is the last significant multiplication that I'm going to perform to my result for iteration, because I want to multiply 5, 4, 3, and 2. I don't need to multiply per 1 because it's going to be simply redundant. Now, with the recursion, the thing is that we don't have a variable in which we stock initially the value 1, like in iteration here. We don't want to indeed use variables here. So look carefully what I'm doing. I do if the initial input is 0, so 0 is equal to NB, or 1 is equal to NB. For me, this is the base condition. This is the exit condition, and I will return something. I will return 1, okay? Because we know that factorial of 0 and 1 is 1. Cool. Here I want to exploit the magic of recursion. In which way? Well, you know that when we say recursion, we imply calling the same function inside itself. So I say return factorial with the value, the initial input, which is 1 less. Let's pretend I have 5 here, like in my example. This recursive call is going to handle all these values. It's going to handle 5, 4, 3, 2, and that's it. Okay, so I have 5, 4, 3, and 2 inside this else block. Here, of course, I'm going to handle 1 and 0. Now we're going to see on CTutor, so you have a better grasp. But basically, I have a function that is handling the value 5, another function that is handling the value 4, another function that is handling the value 3, and so forth. So I'm going to say, please call again yourself with -1. So make a clone of yourself with the value 4. The value 4 is going to make a clone of itself with the value 3, and so forth. This is recursion. This is going to return me a value, okay? And then here, what I have to do? Well, I just have to multiply by myself, by the value that I have inside my function. So per NB. Of course, we have to handle also the negatives. This is going to be another base case, so we do like that. If NB is minor than 0, you return 0, okay? You return 0. This we can change to an else if. Okay, and we're done. We're basically done. Let's try to launch it, and let's see if it works. Okay, let's run factorial. And as you can see, it works exactly like before. I have all the values, like in the iteration case. Now let's try also to put some negatives. I start from -5. here it comes. Of course, I handle all the negatives with 0, with -1, but that's not the point. We're just looking for recursion here. Now let's try to understand better. So as usual, we go to see tutor, which is amazing to understand these ideas of recursion. So we start. The first time we have factorial of 5. So it's going to check this base case. If it is negative, no, it is not. We skip. Is it 0 or 1? Nope, it is not. So what do? You call again yourself, but this time, look carefully. I have nb -1. So I have another function that gets allocated inside the stack with n -1. Boom. I'm going to do all the time these recursive calls until what? Until I will reach factorial of 1. This is a case base, an exit condition that I have. So this is going to return 1, but as you can see, I have all these pending functions inside my stack. Does it seem familiar to you, this pending stack? Well, of course, my friend, is this operation, you see? Is this operation. So I have all this multiplication. I have the case base that is turning me back a 1. Okay, returning 1. And now I'm going to resolve this final operation because all the pending functions are waiting for a return value from the recursive call per nb, but every function call has its own nb, which is 2, 3, 4, 5, and so on, you see, depending on the first input. So I'm going to have all the multiplication coming back, and boom, I have 120, which is exactly the factorial of 5. I hope you understand the point. It's not super simple to understand recursion, but with a lot of practice, you will master it, I'm sure. And of course, I have my personal gimmick to do this stuff. If you want, just check my video. Keep in mind that recursion, performance-wise, is no better than iteration. It is sometimes crispier to write code with recursion. For example, look at this code. You just write these lines, and you're done. That is factorial. It's very crispy, right, to write code in this fashion. Anyway, let's move on. Let's do another exercise. Now, let's do power. So I'm going to do power, let's see. Of course, you know what is power, right? 2 elevated to 8 is simply repeated multiplication. So you see, you have something that is repeating. And all the times when you have something that is repeating, you can think about recursion or iteration, okay? Recursion is repetition for any practical purpose. So we are not gonna deal with negatives to make it simple, even though it's pretty simple to implement, and as well as overflows. We don't care. Another thing is that 0 elevated to 0 is equal to 1, as well as every number elevated to 0 is equal to 1, right? Why is that? Again, my friend, here we have the solution. I will link this video. Liquid gold, my friend. He explains very well this mathematical concept. So let's write a little main test. Main, so for int I equals 0, let's do -5. So we're gonna do powers of 2 in my test, okay? Easy to spot immediately. Cool, let's implement the function. First of all, iteratively. So int power, we have nb and power, okay? Well, iteratively, the solution is pretty close to the one of factorials, right? We create a variable, result, which is an integer, and inside the result, we're gonna put a neutral value for multiplication, which is 1. And I say while what? While power, for example, is major than 0, what do? You just go to accumulate inside the result variable the multiplications, so per equal nb, okay? Then you are gonna decrease power. You're gonna decrease power by 1. So you see what I'm doing? Let's say I have 2 to the 4th. I say until power is major than 0, so until I have 4, 3, 2, and 1. All these cases are gonna be true. I say until this is true, you perform the multiplication of result per nb. So I have 4 times the multiplication of 2, you see? I have 2 per 1 equal 2, and 2 per 2 equal 4, 2 per 4 equal 8, 2 per 8 equals 16, okay? And then I simply return result. Here you understand that 1 is important. I cannot put 0, otherwise the result is gonna always be 0. I need a neutral value for multiplication. Now, of course, I have to handle the negatives. So I'm gonna do if nb is minor than 0, you just return -1. And of course, also the case by which the power is equal to 0. So 0 is equal to power. You just return 1, okay? as a mathematical rule. And I think we are ready to rumble with our power function. Of course, here I have to call my function my power, otherwise it's gonna conflict with the real power function. Now in my main I call my power. Okay, let's compile and launch run power. So I get all these ones. Let me change a little bit. I have minus, let's do like that, %d, and here I put I. So let's watch again. Let's launch. Okay, all my negatives are gonna return me 1, not -1. Oh yeah, here I've written NB, but it is power, not NB. Okay, let's just run again, and as you can see, I have 2 to the 0, 1, 2 to the 1, 2, 4, 8, 16, 32, 64, 128, and so forth. These are, of course, the power of 2. Cool, easy peasy, right? Now let's do with recursion. So I'm gonna comment this, and let's check the problem again. Now, as always, let's make case base exit condition. So if something, you are finished with the calling stack of functions, else you're not finished and you have to do recursion. This is the basic blueprint of recursion. Every time you do like that, then maybe you can zoom out a little bit and engineer better your code. So here I would say that the input can be negative, 0, or positive. So when it's negative, I have another exit condition, right? I don't want to deal in our implementation with negatives. So I need another case, which is if power minor than 0, you just return -1. Finished. I don't want to deal with that. Okay, this is one case base of returning. We don't want to deal with negatives. On the contrary, the number can be 0 or more. So in these other cases, what can we do? Well, here I can have, for example, when the power is equal to 0, okay? We can say if 0 is equal to power. For example, if we have 2 to the 0 or 0 to the 0, you always get 1. So you just return 1. Return 1. Okay, this can be the condition. Else is the recursive part, the difficult part, the place in which we have a repetition of something. So given that I have my case base that is handling only 0, here I have all the powers in a range n to 1, right? Because 0 is going to be handled by the case base. So let's pretend I have 2 elevated to the 4th. Here I will have power 4, 3, 2, and 1. So I can do something like that. Return recursive call with the same number, of course, but with the power that is going down. So power -1. Okay. So let's try to understand now what we have to do. After I call the recursive call, here what is the final operation? Let's pretend I have the power 4. I have the power 4, so I skip this, and I get here, I call again myself, power 3, and then power 2, and then power 1. I call myself again, and then I return 1. So I have all my pending functions inside my stack that are waiting. And here, with the last function before the case base, I have a 1, right? I have a 1 that is coming from the case base. What shall I do with that 1? And you have to keep in mind that you have 4 functions that are pending inside the stack. My friend, you have to perform 4 multiplications, right? You have to perform 2 per 2 per 2 per 2. This is 2 to the 4th. So what do you do here? Well, you have to say and b. I guess that's it, my friend. Let's try to launch and let's try to understand and convince ourselves that it works. So round power. For all the negatives, as you can see, I have still -1. And then I have all the true powers, as you can see, right? It works. Essentially like iteration. 2 to the 8, of course, 256 and so forth. Now again, let's try to watch the code in C tutor, which is the best thing to do. Let's start with the first value, which is 2 to the 5. Is power -0? No, it is not. We skip that. Is my case base, namely 0, is the power? Nope. So you have the recursion. So you have the recursion, and every time you decrease the power until you reach power is equal to 0. Okay? Look how big is the call stack. We reach the bottom with power is equal to 0. So as you can see, I exploit the stack discipline as a data structure to perform a multiplication. I hope you can see that. I have 2 per 2 per 2 per 2 per 2. Because now I have a return 1 inside my else if, and all my pending functions that are waiting are going to perform the final operation, which is return the value given by the case base per NB. Every time I'm going to have per 2, per 2, per 2. See? Per 2, per 2, per 2, per 2. Boom, 2 to the 5 equal 32. Perfect. Now, it's kind of tricky to understand recursion. I pledge you to do by yourself. You watch the video and just practice, and that's the only way out. No video can really help you, frankly speaking. I myself had to understand from a practical standpoint. I haven't never seen a video that really made it click like that. That's not the thing with recursion. All right, that's it, my friend, for these exercises. Thank you. Enjoy.